Hello to our friends joining us via recording. We are preparing for the final exam. The final exam includes content from each of the 4 units this semester. So today we're going to kind of bounce around between some of those units and talk about some of the ideas that we'll see on the exam. One of the things that we'll see on the exam is the different kinds of transport processes that the cells in our body use to move things. So 3 of the transport processes that we talked about with our groups today was the process of diffusion, the process of osmosis, and the process of active transport. We're going to build a compare and contrast table here with this information to help us remember what's going on with each kind of transport. So I want to start here actually in the middle of our table with the type of transport called osmosis. When we talk about osmosis, there's a very specific thing that moves in osmosis. What moves in the process of osmosis? What's moving? Yeah, the only thing that's going to move through osmosis is water. So when we talk about the process of osmosis, what's happening is water is going into or out of a cell. One of my groups was talking about how we had that terminology in your packet about how water follows salt. So wherever I have more salt, whether it's inside the cell or outside the cell, water is going to go there. It's going to try to dilute things down. So in osmosis, water is what moves. When I talk about the process of diffusion, we said before we went into our groups here that there's actually 2 kinds of diffusion. So I'm going to use different colors for them. Let me outline my colors here. So we're going to have regular diffusion that I'm going to put information for in red. And then we're going to have what's called facilitated diffusion. And I'm going to put that information in orange. When I talk about either the process of diffusion or facilitated diffusion, am I moving liquid, called the solvent, or am I moving the stuff that's inside of it, called the solutes? That's some terminology. Let me type those words for us. Solutes and solvent. There's a note for us. The solvent is the liquid, and the solutes are the stuff in it. Yeah, so when I'm talking about either of my processes of diffusion here, diffusion helps us to move solutes. Solutes move in diffusion. When we talk about osmosis, it's the solvent, it's the liquid that's moving. Now, when we're comparing regular diffusion to facilitated diffusion, there's a difference between these transport processes that this word facilitated helps us to recognize. What's going on in facilitated diffusion that's different from just regular diffusion? What's this facilitated thing mean? Yeah, Gloria's totally right. When I talk about facilitated diffusion, I'm going to abbreviate that FD, facilitated diffusion, we do use a protein to transport things. It's going to be a protein that moves stuff across the membrane. I have to use facilitated diffusion sometimes because I need to get something across the membrane that normally the membrane says you shall not pass. Normally the membrane says I'm not going to let you through. Let's bounce back to diffusion here, because in diffusion things just go straight through the membrane. Regular old diffusion, you go straight through. What were some of those words that we talked about to describe things that can do regular diffusion, that can go straight through the plasma membrane, no protein required? What are some of those words that we use to describe that stuff? Yep, here they come. That first word, nonpolar. Nonpolar, The synonym, or what means the same thing, was hydrophobic. We don't like water, and things that are really small. Things that are really small. The process of regular diffusion, where we go straight through the membrane, I can do that with things that are nonpolar, things that are hydrophobic, they're afraid of water, and things that are really small. Sometimes, though, I want to move stuff that is not nonpolar. I want to move stuff that is polar. Here's my first description of what moves here, something polar. Or maybe I want to move something that's hydrophilic. It really likes water. Or I might be moving something that's a little bit larger. It's not super small. These are the kinds of things that I'm going to need a protein to help me move across the membrane. So if I'm moving something that's polar, if I'm moving something that's hydrophilic or something that's large, I could do that with the process of facilitated diffusion. In regular diffusion, we just go straight through the membrane because we match the membrane or because we're really small. In either of these diffusion processes, I asked you about the direction that things move. When I say direction, I mean, are we going up the concentration gradient or down the concentration gradient? Which way are we going with either kind of diffusion? Both diffusions, it's the same. We're going up the concentration gradient or down the concentration gradient? Yeah, so for both of these, we're going down the concentration gradient. Or the other way to put it, like Nicole mentioned for us, we're going from where there's a lot of something, high concentration, to low concentration. So in both diffusion and facilitated diffusion, we go from high concentration to low concentration, or we're going down the concentration gradient. Since both of these are going down the concentration gradient, do we need energy to go down? Is energy required? Yeah. No energy. No energy required, oops, for either of these processes. Because both of them are going down the concentration gradient or going from high to low, we don't need energy to do either of these processes. When we talk about the process of osmosis, did osmosis take energy? Is there energy required for osmosis, the movement of water? Yeah, no energy here either. So no energy for the process of osmosis. That means since there's no energy required, we must also be going from high to low when we talk about osmosis. Now, here's a thing to remind you of, something that make sure you check out after class today. When we talk about how osmosis, we're going from high to low, keep in mind that I'm talking about, I go from a place where there's a high water concentration to a place where there's a low water concentration. So water moves from where there's not a lot of salt, where there's a lot of water, to where there's more salt, where there's not as much water. Make sure to review that, because I know it was a little bit tricky for us back when we were first talking about osmosis. In osmosis, what moves is water, and water is always going from where there's a lot of water to where there's a little bit of water. When we're comparing numbers on salt, it's going to look a little funky. So look into that and make sure we're reviewing. In general, the process of osmosis, did we say that osmosis needed proteins? Do we need proteins to do osmosis? Yeah, water is really small, so we don't need proteins to do osmosis. We can pass these really small molecules through the membrane too. So osmosis is the movement of water across the membrane. We go from where I have a lot of water to where I have a little. No protein required and no energy required either. When I get to active transport, its name tells me right away that I need something. What do I need based on the name active transport? Yeah, I've got to have energy, right? So yes, there is energy involved in active transport. There are two kinds of energy. I think we'll be able to talk about these today. Remember, there are two kinds of energy that we can use to move things across the membrane. The first one is ATP, that chemical energy that your cells build. The other kind of energy that we could use, though, is the energy of another concentration gradient. If you remember when we talked about the transport processes, we kind of called this piggybacking, where somebody is going down their concentration gradient, I jump in with them, and it helps me to go up my concentration gradient. So I use some kind of energy, whether it's the chemical energy of ATP or whether it's the energy of another molecule that is going down their concentration gradient. I'm going to use energy to make this happen. If I'm using energy to make this kind of transport happen, I am going to have some proteins to help me do that. Because see, when I'm using energy, that means, let's do another one here, I'm going from low concentration to high concentration. I'm going from somewhere where there's not a lot of me to somewhere where there's already a lot of me. I can't do that except by using energy. And if I'm moving the wrong direction, essentially, and I'm using energy to do it, I need to use a protein to help me do that. Whenever we do active transport, when we're using energy to move something, we are definitely going to have to use proteins to make that happen. And actually, we're going to talk about today the specific kind of proteins we have to use to make this happen. If I'm using energy to move something, I have to use the kind of protein that attaches to what it's transporting and changes its shape. Which of my kinds of transport proteins attached to what they were moving and changed their shape? Yeah, exactly. When we talk about the kind of proteins that attach to what they're transporting and then change their shape, their special name, they're called carrier proteins. So for me to do active transport, I must use carrier proteins. That's the only way I can move something from low concentration to high concentration. Over here, when we're talking about facilitated diffusion, and we're talking about the proteins we use over here, when we do facilitated diffusion, the kind of proteins that we're using over here are channel proteins. Channel proteins. These could be leakage channels that are always moving things from high concentration to low, or they could be gated channels where I only occasionally move things from high concentration to low concentration. But either way, when we're doing facilitated diffusion, we use channel proteins. When we're doing active transport, we use carrier proteins, where we have to attach to what we're transporting. When we think about what's moving in the process of active transport, we talked about a few specific examples of the kinds of things that we moved in active transport. Did either of my groups happen to figure out what were some of the specific things that we use active transport to move? What did we say we moved in active transport? Okay, yep, so one of the things that I do is I move ions in active transport. In particular, it's some of the ions that we're getting ready to talk about with my neurons and with my muscle cells, so sodium and potassium. And there was one other thing that's really important for your cells, that we used secondary active transport to bring inside. Yeah, Nicole's right for me. That other thing that we use active transport for is glucose. Why do cells like glucose, by the way? What's the big deal with glucose? Why does it matter? Yeah, glucose is a cell's favorite food. This is the easiest way for it to make ATP, to make energy. So I'll use some energy to be able to get my food that I need so I can make more energy. So active transport, when I move my ions, sodium and potassium, the wrong direction, or when I move glucose inside, even though I've already got a lot of glucose inside, when I go from low concentration to high concentration, that's going to take energy. And if it takes energy, I'm going to have to use a carrier protein. So there was a quick crash course for us. Reminder about 4, I guess, of our transport processes. Before I move on from this slide, any questions that we have about these processes? Yeah, go for it, Gloria.
Okay, so in facilitated diffusion, it still moves down the concentration gradient, right?
Yes, yeah,
Okay.
that's correct. It's just that the thing that I'm moving down the concentration gradient, my membrane isn't going to let it go through on its own.
Right.
So remember that the only things that can sneak straight through have to match the middle. If I'm trying to move something that doesn't match the middle, but I still want to move it from high concentration to low concentration, I can do that using a channel protein to pass it through.
Okay, perfect. Thank you.
All right, so there was our first compare and contrast. Let's do our second compare and contrast. This was the 2 types of tissue that we talked about how they worked. So this was unit number 3 here, when we talked about the process of muscle contraction, and we talked about the ways that nervous tissue talked to each other, or my neurons talked to each other. I didn't make you memorize a lot of numbers this semester, but we do have to know a few numbers related to these types of tissue. One of the numbers that we need to know is what's called their resting membrane potential, their normal charge when they're waiting to hear a message, or when they're waiting to contract in the case of muscle tissue. When I talk about muscle tissue, what's my resting membrane potential? My normal charge when I'm not contracting. Yeah, so a couple of us are chiming in. In muscle tissue, my resting membrane potential is -90, -90 millivolts. That's different from what I see in nervous tissue. What's the resting membrane potential on nervous tissue when a neuron's waiting to hear a message? Yeah, neurons, when they're waiting to hear a message, they're chilling out at -70. So neurons a little bit less negative compared to muscle tissue. Make sure we know these 2 numbers. Muscle, -90, neurons, -70. And technically most cells in your body at -70. But the 2 numbers I got to know, -70 for nervous tissue, -90 for muscle tissue. When my muscle cells are completely depolarized, meaning when we are at the top of that membrane charge graph, how high, or what's the depolarized charge that I see the muscle tissue membrane getting to? Yeah, muscle cells go all the way up to +30 millivolts. Hey, what do neurons go up to when they're completely depolarized? What's their charge when they get depolarized? Yeah, their charge is exactly the same. Maybe love things that are the same, right? It's one less thing to memorize. We start at different resting membrane potentials, but at the end, when we're completely depolarized, we both go to positive 30. Our membrane charge completely freaks out. It's completely wrong. Hey, something else that's the same is the ion that I use to get to positive 30. Which ion do I use in muscle tissue and nervous tissue to get my membrane charge to positive 30? Yeah, so for both of my types of tissue, I'm using Na plus or sodium to get me to positive 30. Na plus, sodium. Hey, let's do a reminder here. Sodium, more of that inside or outside? Where's there a lot of sodium? Yeah, lots of sodium on the outside. That means that when I open up a channel protein for it, sodium's coming in or going out. How's sodium going to move since there's a lot of it on the outside? Yep, rushes in. Sodium rushes in. Note here. In both muscle tissue and nervous tissue, when it's time for me to, it's called get excited. These are excitable cells, change their membrane charge. In either of them, when I'm changing their membrane charge, sodium is going to rush into those cells, get us all the way up to positive 30. Now, when I'm at positive 30, that's the wrong membrane charge completely. I'm going to repolarize my membrane to get it back to normal. Hey, I use the same ion to repolarize my membrane in both of these types of tissue as well. What's the ion that I use to repolarize both of these tissue types? Yeah, exactly. I'm going to use K+, which is potassium. K+, on the other side here. With potassium, is that going into a cell or going out of the cell? Which way is potassium going? Yeah, potassium is rushing out, rushes out. When potassium, with its positive charge, leaves the inside of the cell, the inside of the cell's membrane gets more negative. It helps me go back to my resting membrane potential. So both muscle cells and nervous cells use sodium to depolarize. We go all the way up to positive 30. Then we need to repolarize with potassium. Lots of similarities between these two. One way that they're different, though, an important way that they're different, is what happens or what calcium does in this process. When I talk about the role of calcium, let's start with nervous tissue. When I talk about the role of calcium and when neurons are functioning, what's the role of calcium in the way that neurons do their job? What does calcium help neurons to do? Yeah, exactly. So calcium, when it rushes in at the axon terminal, we spit out neurotransmitters. Spit out neurotransmitters. Remember, we kind of talked about calcium as allowing us to talk to our neighbor, essentially. Neurons talk to each other using neurotransmitters. So when calcium is pulled into a neuron at its axon terminal, at the axon terminal, we spit out neurotransmitters. We talk to our neighbor. Muscle tissue doesn't really communicate with other cells. Muscle tissue gets stuff done, right? Muscle tissue does contraction. How does calcium relate to the process of muscle contraction? What specifically does calcium do in the process of muscle contraction? Yeah, so calcium is an ion that's going to attaches to a protein called troponin. Troponin was a regulatory protein, meaning this is a protein that determines whether or not a muscle contracts. When troponin is not attached to calcium, it's acting like a push pin and it's preventing the whole process of muscle contraction. When calcium attaches to troponin, troponin changes its shape, which means that it's no longer pinning into place tropomyosin, which is that spaghetti noodle that blocks myosin from attaching. So when I have calcium, big picture, my function of calcium is to start the process of contraction. By messing up those regulatory proteins, by stopping regulation, we allow contraction to happen. So compare and contrast here with muscle tissue and nervous tissue. A lot of things about the way that they function are the same. What we use to depolarize, what we use to repolarize, where we go when we're depolarized. Make sure you know that their resting membrane potentials are different from one another, and make sure we know in particular what calcium does for these two things. It helps us to start contraction when we're talking about muscle tissue, and it helps us to spit out neurotransmitters when we talk about nervous tissue. Nicole asked a question about the thing called threshold. Let me type that, threshold. Threshold in a neuron is -55 millivolts, -55. Remember that threshold is the charge that if I get here, if my membrane gets to -55, I'm going to completely depolarize. So reach this, then depolarize. This idea of having a threshold value actually only applies to nervous tissue. With muscle tissue, whenever it receives a neurotransmitter, it will always at least partially contract. So say we receive 2 neurotransmitters. A neuron spits out 2 of them. That's not going to bring in very much sodium. I might just contract a little part of my membrane, but maybe instead of getting 2 neurotransmitter messages, I get 20 neurotransmitter messages. Now I'm going to have a really strong muscle contraction because I'm going to bring in a whole bunch more sodium across more places in my membrane. So with muscle tissue, if you send any kind of message for contraction, at least part of the, here's a muscle word for us, at least part of the sarcolemma, the plasma membrane of a muscle cell, will depolarize, which will lead to at least some of the myofibrils contracting. If you want your entire muscle fiber to contract, though, you're going to need to spit out a lot of messages. So there's no threshold for muscle tissue. Sometimes with muscle tissue, we call it all or nothing. Either you're getting a message and you are responding to it, or you're not getting a message and you're staying relaxed. So no threshold value for muscle tissue. That's just something we see with nervous tissue. Good clarifying question. Any other questions before we move on? Shoot me some emojis. How are we thinking this? What are we feeling? We got Mushu. Gotta love Mushu. I'm gonna look here for an emoji. I'm liking this. I'm liking the fact that it's kind of raining today. Rain makes me happy. Okay. Yeah, Hannah said it's sleeping weather. Alas, there's not nearly enough sleep though, right? This is, it needs to do this again on like Wednesday, right? When we've all taken the anatomy final exam and we can actually sleep, right? That's when it needs to rain some more, when we can enjoy it. Sorry about your back pain, Monica. That's the worst, when the weather makes things like that worse. For your sake, we need it to stop raining, right? Okay, so what I want us to do, since we've talked about these ions involved in muscle tissue and nervous tissue, I want us to kind of relate this to the things that we talked about with muscle tissue and nervous tissue. This is lesson number 9. You have this picture in your lesson number 9 packet. We already summarized this information on the table we just talked about, but I want to point out and mention to you, we use sodium, I know it's really small, but it says Na+, sodium channels to depolarize the sarcolemma on a muscle cell. When we get all the way up to positive 30, at that point, we're going to repolarize the membrane using potassium. Our favorite, or my favorite, salty banana, reminds us that sodium comes in to a cell, making the membrane charge go up. Potassium leaves the cell, making the charge go down. What starts the process of muscle contraction is a chemical messenger, specifically the chemical acetylcholine. That means that in a muscle cell, which kind of ion channels are we opening at the beginning of this process? If I use acetylcholine to open them, which kind of channels open with acetylcholine? Yeah, so a couple of us have chimed in the chat. Acetylcholine is a chemical, so I use chemically gated channels. They bring in some sodium. They start to depolarize the membrane. Remember, we talked about the thing called the action potential, where I depolarize one part of the membrane and then I freak out all the parts that are next to it because they have those voltage gated channels. But remember, in a muscle cell, or while we're at it, in a neuron, it all starts with chemicals, with chemically gated channels. So here's Dr. Ollis's favorite graph, the one that pops up almost every unit. I guarantee you 100% you will see this graph on the final exam. There's just no getting around it. Let's remind ourselves of what this graph shows, and then we'll pair it up with our ion channels that we've already talked a little bit about here. Remember that neurons, when they're at rest or at their resting membrane potential, they are listening for a message from their neighbor. They're listening for a stimulus. So a stimulus is a fancy word for a message. When a neuron receives a stimulus, when it receives a neurotransmitter, that neurotransmitter may help to bring its membrane charge up to threshold. Threshold. Now remember, that was one of the other numbers I wanted you to know. For neurons, we have this threshold value of negative 55 millivolts. If I get to negative 55 millivolts, that tells my membrane we're serious enough about getting positive that we're going to go all the way. So if we hit negative 55, we're going to completely depolarize. If we stay under negative 55 down here, we won't depolarize. For me to be able to talk to my neighbor, like we see our little chat bubble up here, for me to be able to talk to my neighbor, I've got to get to positive 30. So for me to be able to talk to my neighbor, I first have to hit threshold. I first have to get to -55. When I get here, I'm going to rush in a whole lot more sodium until I'm completely depolarized, at which point I realize, oh, this is completely wrong. I can't stay here. I spit out a bunch of potassium to get me back down to my regular charge. Although remember, I do a bad job at stopping spitting out potassium. So there's actually this period on my graph that we can see right here where my membrane charge is a little too negative because I spit out potassium longer than I needed to. Over time, I'll use my leakage channels and my sodium-potassium pump to get back to resting membrane potential. Hopefully this graph makes a lot more sense now than it did in unit number 1. We've talked about it a lot of times. Let's use the picture from lesson number 10. Make sure we can remember which kinds of channels open when, or what kind of channels are used in different places. We just talked about this. When I'm below threshold, my channels that open and close down here are the ones that respond to neurotransmitters. Which kind of channels are opened by neurotransmitters? Which kind of gate is open with neurotransmitters? Yeah, it's those chemical gates. Down here below threshold, we have chemically gated channels, meaning the right chemical is going to open up my gate. When I hit threshold, my charge is different enough that now I start to mess up my voltage gated channels. My charge is wrong. Which particular kind of voltage gated channels open at threshold? Yeah, here at threshold is when my voltage gated sodium channels open up. Sodium, Na+, A+. There we go. Voltage gated sodium channels, the voltage or the charge that they open at is -55 millivolts. When they open, because there's so much sodium outside, that sodium is going to rush inside and bring its positive charges with us. So all along this depolarization side of the graph, all along over here is all those voltage gated sodium channels. They first open at threshold because the charge is different enough. They're open all the way through this depolarization stage, all the way until we get up here at the very top. Now we're completely depolarized. My charge is completely wrong. There are two kinds of channels that open when my charge hits +30. The first kind that's going to open is a voltage gated channel that I use to repolarize the membrane. Which kind of ion did I use to repolarize the membrane? Yeah, potassium. First kind of channel that opens when I am completely depolarized is voltage gated potassium channels. They open at +30. They stay open, voltage gated potassium. They stay open all through this process of repolarization because their goal is to get the membrane charge lower and lower and lower. So we first open voltage gated potassium channels when we're at +30. We keep them open all the way through here. They take their sweet time slowing down to close, which is why I get a little bit too negative. I go down into the period down here called hyperpolarization. Let's go back up here though to depolarized. When I'm completely depolarized, the other thing I need to do is I need to talk to my neighbor. What was the ion that we said helps a neuron to talk to its neighbor? Yeah, this is where, remember from our previous slide, our comparison, this is where calcium comes into play. Voltage-gated calcium channels also open at positive 30. When calcium comes in to the axon terminal, neurotransmitters spit out. So I talk to my neighbor when my membrane charge gets to positive 30. But again, I don't want to stay at positive 30. I want to get back down to normal. Voltage-gated potassium channels get me back down to normal. Then I go a little bit too far. I get that hyperpolarization thing going on. To get me back to normal, we use two kinds of channels. The first kind of channel that you see on our list there are those things called leakage channels. Because my charge is too negative, I will leak things back and forth to get my charge back to regular resting. I can also use something called the sodium-potassium pump. The sodium-potassium pump. And the sodium-potassium pump is an example of primary active transport. Primary active transport, and we'll look at it here in just a moment. But in primary active transport, I have to use ATP. I've got to burn some of my energy monies, we called it, to get me back to normal. That tells you just how important it is that your cell be at negative 70 millivolts. To get me back to my normal resting membrane potential, I'm willing to use my energy monies for that. So leakage channels and the sodium-potassium pump help me get back to resting membrane potential. Before we move on from this graph, do we have any questions about it? Okay, sounds like we're feeling good. Awesome. So let me just mention one more thing for us then related to this graph, related to that beginning part of the graph. Remember that before a neuron hits threshold, it's doing the process where it adds together all kinds of different messages. What was it called when a neuron adds together a bunch of messages? Yeah, a bunch of us actually beat me to the question. We knew where I was going. The process that we see in this picture here, we're seeing the process called summation. Summation, where we add together some positive messages, shown in green, with some negative messages, shown here in red. When we talk about positive messages, Epsps, these are excitatory. So excitatory messages, they make the membrane charge go up. So I receive a neurotransmitter and it gives me a positive, or it gives me a bump in my membrane charge. That's an Epsp when my charge goes up. I could also receive a message though, or a neurotransmitter that causes an Ipsp. That's an inhibitory message that makes my membrane charge go down, or it pulls me away from threshold. Because remember, for me to be able to talk to my neighbor, I have to hit threshold. We've got to get to threshold to be able to go all the way up to positive 30. If I never make it to threshold, I never talk to my neighbor. So summation is the process that I use to add together all the different kinds of messages I'm receiving to figure out if I'm going to get threshold, to figure out if I'm going to go all the way positive. When we talk about Epsps and Ipsps, these little changes in charge, do we remember, are these caused by chemically gated channels or voltage gated channels? which kind of channels help me to do EPSPs and IPSPs? Yeah, so this kind of stuff that we're talking about here, when we are below the threshold value, everything that happens down here, all my small positives and small negatives, all of these changes that I see happening, this is all due to chemically gated ion channels. Like someone mentioned in the chat, totally right. It's not until I hit negative 55 that I start to use the voltage gated channels. So when we talk about, if I were to ask you a review question, or if I were to ask you an exam question about which kind of ion channels could help me to generate EPSPs, excitatory postsynaptic potentials, make sure that you tell me that excitatory postsynaptic potentials are from chemically gated sodium channels. Chemically gated. Because if we talk about the voltage gated sodium channels, those are the ones that completely depolarize the membrane. Voltage gated do all of this business. Everything below threshold, that's my chemically gated channels. If I ask you about the type of channels that generate IPSPs, now we're talking about two different options. There's two ions that help us do IPSPs. What were the two kinds of chemically gated channels that would help us to generate IPSPs? What ions make the membrane charge go down? Yeah, so there's two of them, right? The first one we've talked a whole lot about already is potassium. The other one, though, when we're talking about making IPSPs, is chloride. I've got two different kinds of chemically gated channels. I can either let chloride into my neuron, or I can spit out potassium. Either way, my membrane charge goes down. But the only way I can make these things move when I'm below threshold is using a chemically gated channel. So, big picture, keep in mind, whenever we talk about summation, summation is all about those chemically gated channels. It's all about using those chemical messages that we received to help us know whether or not we should completely depolarize. One of the correlations related to these chemically gated channels that we talked about was we talked about sarin gas. I had a couple of people request that we talk about sarin gas. When we talked about sarin gas, big picture, something for you to keep in mind. Sarin gas messes up the process of neurons talking to muscle cells, and it can also mess up the process of neurons talking to each other. See, when we talk about muscle cells or when we talk about neurons, both of them have this enzyme on their membrane called acetylcholine esterase. Acetylcholine esterase. Can you help me out in the chat? What's the job of acetylcholine esterase? Acetylcholine esterase, ACHE, the esterase one. Yeah, exactly. Esterase means that we're breaking something down. Specifically, what this enzyme does is it breaks down the message acetylcholine, ACH. Remember that acetylcholine is my chemical that a neuron spits out, and it goes down and it attaches to my chemically gated channels on the membrane of a muscle cell. Once that chemical opens up the chemically gated channels on a muscle cell, we will start an action potential and that muscle cell will contract. But once I've started that that process, I don't want to continue to respond to this message. I use an enzyme embedded in the membrane called acetylcholine esterase to chop up that message. When I chop this message up into little pieces, it can't open up any more chemically gated channels. I hear the message once and then I recycle it. I'm done hearing it. The problem with sarin gas is sarin gas inactivates this enzyme. Excuse me. No longer can acetylcholine esterase chop up acetylcholine. Now that acetylcholine that opened up this chemically gated ion channel is going to float around in the synaptic cleft and find a new receptor over here, and it'll attach to that receptor and start the process of muscle contraction again. And then it'll float a little bit farther and it'll find a new receptor and start the process of muscle contraction again. The problem with sarin gas is I keep hearing the same message over and over and over again. My neurons still spit out one neurotransmitter, but my muscle cell hears it like 5 times. And then if my neuron happens to spit out another message, I'm just going to keep hearing the first message and the second message. And I end up contracting way too much, all because my recycling mechanism, my acetylcholine esterase, can't chop up those messages anymore. So sarin gas messes with the way that my chemically gated sodium channels work. I keep those chemically gated sodium channels open too much, and my muscles contract too much. What questions do we have about sarin gas? Yes, soaking it all in. Question in the chat if sarin affects the ability of our muscles to build acetylcholine esterase. It doesn't have any effect on building that enzyme itself. It just inactivates the enzyme that's there. And it's not permanent necessarily. Over time, the sarin gas will actually let go of this enzyme and let it go back to doing its job. But if you have a really massive sarin gas exposure, your symptoms may be too severe before acetylcholine esterase is working again. So the question is if we're inactivating acetylcholine, we're not doing anything to the neurotransmitter. So acetylcholine itself, we're not messing with it. That's doing its normal thing. What we're messing with is the enzyme that breaks it down. So we're messing with ACHE, acetylcholine esterase, the enzyme that breaks things down. If I can't break it down anymore, this neurotransmitter stays active longer. It keeps sending a message longer than it's supposed to. So it's kind of the opposite of inactivating acetylcholine. We leave it around forever, and then we really respond to it too much. Okay, so we are at an inflection point, if you will. There are a couple of different directions that we could go right now. I had some requests for us to talk about water intoxication, and then I had requests for us to talk about the different kinds of protein channels. I think we're going to have time to talk about both of those things in the amount of time we have left today. Which would we rather talk about first? Water intoxication or protein channels, proteins in general? Got a couple votes for proteins? Okay. So we're all voting proteins. Let's do those, and then we'll bounce back to or circle back to water intoxication briefly toward the end. You know how I do love my compare and contrasts. So to help us with our discussion here of proteins, we'll work together here on finding how things are similar and how they're different to one another. So over here on the left, I am looking at a protein that is open on one half and closed on the other half. It's attaching to what it's transporting and then changing its shape to let that inside. Which kind of protein transporter am I seeing here? Is this a carrier or a channel protein here on the left? Yeah, my one over here on the left is a carrier protein, My one over here on the right then, by process of elimination, this is going to be a channel protein. So channel proteins have a protein channel in the middle. They have a space that is always open, that things can pass straight through. So we've already kind of identified and used the picture to help us determine the big way that channel proteins and carrier proteins are different from each other. It has to do with the way that they transport things. That's the biggest difference between these things. So the way that a channel protein transports things, channel proteins, we'll just call them channels. Channel proteins don't attach to what they move. They don't attach to what they move. So we can see in our picture over here, my channel. That channel is the passageway for the molecules on the outside to sneak inside. Channel proteins are not attaching to what they moved. When we talk about carrier proteins, I cannot spell this morning. Carrier proteins do attach to what they move. Carrier proteins are attaching to what they move. When I talk about carrier proteins, the other thing that they do that we mentioned with our picture is they change their shape. So when we talk about changing their shape, they're open on one side, then the other side. They take turns being open. First, we're open to the outside to attach to something that we're moving. Then we open up to the inside to spit it out. Then we open back up to the outside to attach to what we're moving. Then we open back up to the inside to spit it back out. If my carrier protein is constantly opening on one side and then the other side, that's an example of a carrier protein. Channel proteins always have a channel for things to move through. That channel could be gated. It could be not always open, but once I open that gate, things will pass straight through it. Can we think of any ways that channel proteins and carrier proteins are similar to each other? Any ideas on how they might be similar? Yeah, so Nicole's honing in on probably the most important similarity, the kind of thing that channel proteins and carrier proteins transport. The chemistry of what we're transporting is the same. So what goes through a channel protein or a carrier protein, this is what I use to transport polar things, to transport hydrophilic things, to transport large things. We have to use a protein of some variety to move these kinds of things into or out of the cell. Because remember, moving these things into or out of the cell is not going to happen straight through the membrane. The membrane's got those little bouncers, those bodyguards that are saying, nope, you can't come through. I'm not going to let you through. So I have to use a protein to get it in. Whether I'm attaching to what I'm bringing in or whether I'm just letting it pass straight through me, regardless, the kind of thing I'm moving fits those descriptions of the stuff that won't cross the membrane. So, similarity between channel proteins and carrier proteins, the kinds of things that they transport, stuff that on its own can't get in or out of the cell. Things that are different between them, the fact that channel proteins are basically just a tube. They're not going to attach to what they're transporting, whereas carrier proteins do attach to what they're transporting. They open on one side and then they open on the other side. The other thing we could add for our description of carrier proteins too, we talked about how carrier proteins help us do active transport. Active transport. Remind me again in the chat, what does active transport mean? What's active transport? Yeah, active means that energy is required. Energy is required. When I'm doing carrier proteins, I believe all of them, or at least the vast majority of them, we're going to have to use energy to do this because we're changing the shape of a protein. So active transport with carrier proteins. Channel proteins are going to be passive transport, like we outlined way at the beginning of class. Passive transport. So no energy required. I might have, as we're going to talk about here in a moment, I might have a gate that blocks my channel from letting stuff go through all the time. But anytime I use a channel protein, anytime I've got an open space, an open tube for stuff to move, it's only ever going to move from high concentration to low concentration. There's no energy required when you use a channel protein. I know we're processing. We've just said a lot. But do we have any questions that you want me to clarify about channels and carriers? Ariel's emoji is going cross-eyed. That happens. Anatomy does that. Okay, well, let's look at our types of channel proteins then. Remember what we said before, and I'm going to type this because this is an important thing for us to remember. All channel proteins do passive transport. This is an underline highlight star idea. All channel proteins do passive transport. You should never tell me on the homework assignment or on the exam that it takes energy to move something with a leakage channel or with a gated channel. Neither of these types of channel proteins require energy. Channels have a tube that stuff goes straight through. When we talk about a leakage channels are like that dripping faucet. When we say we have a leakage channel, would we say that a leakage channel is or is not always open? Are leakage channels always open? Yeah, leakage channels are always open. Leakage. We're leaking, we're dripping. Drip, drip, drip. When we talk about gated channels are not always open. That word gated in their name tells me I have some kind of gate that's blocking my channel. When I open that gate, stuff is going to go through it. It's always going to happen. But when that gate is closed, which is most of the time, when my gate is closed, stuff isn't going to move. So when we talk about gated channels, remember that there are 3 kinds of gated channels. What are the different types of gated channels? Do we remember? We've actually talked about 2 types of gates already today. Yep, so first kind, Gloria's abbreviating CG, chemically gated. Chemically gated. When I talk about a chemically gated channel, what causes that one to open? What opens chemically gated channels? Yeah, exactly. Chemicals. Chemicals open them up. First kind of channel, I can see it right here down at the bottom. This is a chemically gated channel. When the right chemical key attaches, we go from having my channel closed to my channel open, and stuff can pass through when that channel is opened by the chemical key. That's my first kind of channel, gated channel. My second kind of gated channel is a voltage gated channel. When I talk about voltage gated channels, what causes those to open? How do voltage gated channels open? Yeah, the word voltage relates to charge. Voltage relates to charge. So I can see an example of a voltage gated channel right here. Here's my gate down here at the bottom of this channel. Notice that in normal circumstances, when it's negative inside and positive outside, this channel is closed, that gate is in place. When it becomes positive inside the membrane, that gate opens, creating this channel for things to pass through. So a voltage gated channel, we change our membrane charge. Either we go from being negative inside to positive inside, or we could actually do it the opposite too. We could go from it being positive inside to being negative inside. The big thing to know with voltage gated, it's all about charge. When my charge changes, a voltage gated channel will open or it will close. That last kind of gate that I have on my channel proteins, what's that last kind called? Yeah, my last kind starts with an M, right? We got our MGs, our mechanically gated channel. How do we open a mechanically gated channel? How do mechanically gated channels open? Yeah, so mechanically gated channels, I literally push them open, or I use pressure. That's the fancy way to describe it, to get them open. I can see that up here. Here's an image for me of a mechanically gated channel. When I put pressure next to it, that opens up the channel. When there's no pressure next to it, that channel is closed. My gate is closed. Hey, we took all semester to get there, but where were the places in the body that we saw mechanically gated channels? Where did we finally see mechanically gated channels? Yeah, exactly. Mechanically gated channels, that is the star of the show in the ear. So when we're talking about hearing and we're talking about balance, those processes use mechanically gated channels, or channels that I press open. I use pressure to allow me to bring ions in and out. So we talked all about chemically gated and voltage gated channels all semester. And then in our very last lesson, we talked about those mechanically gated ones as well, the ones that I push open. Let me peek here. Yeah, so that's all I've got about channel proteins. Any questions about those types of proteins? Here, let me move my little statement right here. That'll make it make more sense. How they're the same, we're doing passive transport. While we're on the protein train then, let's quickly talk about primary and secondary active transport, because both of these processes require proteins. Which kind of proteins did we say we used to do active transport? Does anyone remember what we said just a bit ago? Yeah, active transport is going to take ATP. What was the special name for the type of proteins that do active transport? Yeah, so Nicole's second thing there, sorry, I missed that, Nicole. The kind of protein that does active transport, remember that we're no longer talking about channel proteins that have an open space all the time. When we talk about active transport, we have to use those things called carrier proteins. Carrier proteins. Remember, those are the ones that attach to what they move, and they change shape to move things. When we talk about active transport, we have to do both of these things. If I'm going to spend energy to move something, I have to be able to attach to what I'm trying to move, and I've got to be able to open on one side and then close to open on the other side. Because remember, with active transport, we're moving stuff the opposite way that it wants to go. We're moving stuff uphill instead of downhill. So I'm going to have to be able to have a special tunnel to do that in. That special tunnel is a carrier protein. When we talk about primary active transport, I do want you to make sure that you know our example of primary active transport is the sodium-potassium pump. The sodium-potassium pump. When we talk about the sodium-potassium pump, it has a really important job. Does anyone happen to remember why the sodium-potassium pump is so important? Why our cells need this protein? Yeah, so this is the protein that helps me to get my membrane charge to resting membrane potential. So this generates resting membrane potential. This is what gets me to my normal membrane charge. So we used it when we got too negative, right? On our graph, you remember that part where it dips down. The sodium-potassium pump helps me get back to resting membrane potential. But also, this is what keeps me at resting membrane potential when I'm waiting to hear a message. Because naturally, my cell membrane, kind of its charge wants to go up or down a little bit. We've got some leakage channels that kind of mess things up. The sodium-potassium pump makes sure that my neurons are always at -70 millivolts. Its job is to give me the resting membrane potential. I'm willing to spend energy monies to do this because I need my membrane charge to be at -70 for me to be able to respond to a message. When we talk about the sodium-potassium pump, and when we talk about primary active transport in general, primary active transport, we have to use ATP, uses ATP. ATP, again, is our energy money in the cell. We got to spend some energy money. When we think about the sodium-potassium pump, and we think about primary active transport, the reason I have to spend energy money to do primary active transport is because both of the ions that move in this process are going up their concentration gradient. So in primary active transport, both ions move up their concentration gradient. Both things are going from where there's not a lot of them to where there's already a lot of them. And you can see that in our picture over here of the sodium-potassium pump. Notice that sodium is going out of the cell. We're spitting sodium out. And remember, our cells are salty bananas. There's already a lot of sodium out here. I'm putting even more sodium out. I'm going up my concentration gradient with sodium. Potassium is coming in to the cell. Again, remember our salty banana, there's a lot of potassium inside the cell already. So both of these ions, sodium and potassium, are moving to where they're already more concentrated. Because they're both going up their concentration gradient, I have to use ATP as my energy to make that happen. But see, compare primary active transport, where two things go up their concentration gradient, to secondary active transport. In secondary active transport, one molecule goes up the gradient. That's why it's active transport. But one molecule goes down the gradient. The one that's going down the gradient or going downhill is the one that's going to provide energy. So molecule going down provides the energy. The way I can push somebody up the hill is because somebody else is rolling down the hill, or somebody else already has rolled down the hill and bumps into me and gives me the energy that I need to go up the hill. Our example of secondary active transport is the thing called the sodium glucose cotransporter. That's another one that we want to make sure that we memorize, the sodium glucose cotransporter. When we talk about the sodium glucose cotransporter, sodium and glucose are both moving into the cell. Which one of these, the sodium or the glucose, which one of these does it take energy to move into the cell? Which one needs energy to move in? Yeah, we're totally right in the chat. It takes energy to bring glucose into the cell because your cell is already trying to grab as much glucose as possible. Remember earlier in our class today, we talked about how glucose is a cell's favorite food. So glucose, we hoard it as much as possible. But if we see any or sense any in our environment, we're going to grab that too and bring that inside. It's going to cost us energy to get that inside. The way that our cell works around that, though, the way that our cell provides the energy for that glucose to come in, is it uses sodium. Sodium's coming inside as well. Remember that there's a lot of sodium on the outside, not a lot of sodium on the inside. Sodium wants to rush inside. Sodium's going down its concentration gradient. As sodium goes down its concentration gradient, where it attaches to its carrier protein over here on the left, there also happens to be a spot where glucose can attach at the same time. When sodium and glucose both attach here, we use the energy, or the fact that this sodium really badly wants to get inside, will piggyback, or the glucose will sneak in at the same time with it. So in secondary active transport, somebody's going down their concentration gradient. That lets out energy. That energy that it's letting out allows somebody else to go up their concentration gradient. Primary active transport and secondary active transport. The two ways I can move things up the hill or up their concentration gradients. Yeah, so we got the clarifying question in the chat that sodium is moving down its gradient. Yes, that's absolutely correct. Sodium, so we'll make a note here. Sodium moves in. There's a lot of sodium on the outside, lots of sodium outside. So sodium naturally wants to go from where there's a high concentration to where there's a low concentration. There's a high concentration outside. There's a low concentration inside. This is an example of passive transport, or no energy required to move sodium inside. What other questions do we have? Yeah, absolutely right. So the energy to get glucose in, so glucose also moves in. Glucose moves in, and we'll say there's already a lot of glucose inside. So glucose needs some energy. The energy to get glucose inside comes from sodium moving down its concentration gradient. Sodium moving down the gradient. Because sodium goes down, glucose can go up. Yeah, you're welcome. All right, in our last couple of minutes, what I want to chat about today is water intoxication. Someone asked me if we needed to know everything about that article. And the answer to that question is no, you don't need to know everything. If you look at the list of learning objectives for the final exam, what I really want you to know from that article is the way that water intoxication relates to hyponatremia. We just need to know that. So to help us know that and be able to explain that, I want to do a quick compare and contrast with you again. Remind ourselves of some of the words that we talked about this semester to help us prepare for that aspect of the exam. Way back in unit number 1, we talked about hypertonic and hypotonic solutions. Hypertonic and hypotonic, these are words that I use to compare concentrations. If I say that a solution is hypertonic, what does that mean about that solution? If it's hypertonic, yeah, Gloria is hesitant. We're all hesitant here. It's been a little while since we talked about this, right? Okay, here, I'll help us out here. When I say hypertonic, hyper means above, or too much. Hypertonic means I have a higher concentration. Higher concentration. Hypertonic. I was talking to a student yesterday. The way I like to remember this is if I give my daughter too much sugar, she gets hyper. Hypertonic solutions have too much or have a higher concentration of a solute. So in our class, when we talked about solutes, we mainly talked about salt and we talked about sugar. So a hypertonic solution has a higher concentration of our solute, of salt or of sugar or whatever else we're dissolving in something. Hypertonic. Hypotonic means we have a lower concentration. Think about the hypodermis. That was the lower layer of the skin. So in a hypotonic solution, we have a lower concentration of sugar or of salt. We don't have a lot of those things in this solution. If I have a hypotonic solution, I don't have a lot of sugar, I don't have a lot of salt, I do have a lot of water. A hypotonic solution has a low concentration of solutes, of the things that are in it, but it has a high concentration of water. Hypotonic, this word refers to my solute concentration. Hypertonic, same thing. This tonic word means we're looking at those solutes. I have a lot of them. When we talk about a hypertonic solution that has a lot of stuff dissolved in it, the easiest way for me to make a hypertonic solution is to add lots of solutes. The easiest way to make something hypertonic is just to keep adding solutes. Remember way back in unit number 1, when we were still figuring out this anatomy thing, right? Way back in unit number 1, we talked about sweet tea and how sweet tea, we can just keep adding and adding and adding sugar to it. We can make it really hypertonic with lots of sugar in it. That's the easiest way to make something hypertonic. The easiest way to make something hypotonic, where the concentration is really low, is to add lots of water. Add lots of water. If I add a bunch of water to my cup, that's going to dilute whatever was inside of it. So when we talk about making a hypotonic solution, that's a solution that has a lot of water and not a lot of dissolved stuff in it. You want something to be hypotonic? Add a bunch of water to it. Compared to where it started, it's going to have a way lower concentration. If I want something to have a higher concentration, the easiest way to do it is just adding a whole bunch of sugar or adding a whole bunch of salt. That will make it hypertonic. When we talk about, here's our article tie-in here. When we talk about water intoxication, what's happening with water intoxication? If a person has water intoxication, what did they do? Or what happened to them? Yeah, so when we talk about water intoxication, basically you got intoxicated or you drank too much water. So drank too much water. Remember we joked about way back in unit number 1 that it's way less fun than alcohol intoxication, right? Water intoxication. We drank too much water, too much water. If I have too much water in my bloodstream, is that going to make so this natremia word right here, natremia means salt. If I drank too much water, is that going to make my salt level seem like it's too high or seem like it's too low if I drank way too much water? Yeah, if I have too much water, my salt is going to get diluted. If I dilute my salt, my fancy word for diluting my salt in my bloodstream, hyponatremia. Hyponatremia. So hypo equals below or lower. Natremia equals salt. Hyponatremia, low blood salt levels. Just like we said, to make something hypotonic, you just add water to it, that dilutes it. To make your blood have hyponatremia, you just drink too much water. So the relationship between water intoxication and hyponatremia, if you drink a bunch of water, the level of salt in your bloodstream goes down. So here, let's see if we could figure this one out. Hypernatremia. What does hypernatremia mean? Any guesses? Hypernatremia? Yeah, too much salt. Too much salt. Our salt concentration is too high. How could we change our plasma to have hypernatremia? How could we make it so that we have too much salt in our bloodstream? Yeah, so Gloria's mentioning not drinking enough water, or we don't drink enough, Maybe to supplement that, yeah, like Christina's mentioning, we don't drink enough to offset how much we sweated. Is that even a word? Is that the past tense of sweat? Sweating, sweated? I don't know. That just looks weird to me. If you don't drink enough water, we're constantly sweating. We're constantly losing water through our sweat and through urine. Yeah, you might be right, Gloria. It might just be sweat, how much we sweat. Who knows? Not enough coffee today. If we don't drink enough to offset how much water we lost when we were sweating, it ends up looking like we have too much salt. Because see, the other way you can make something hypertonic, either you can add more salt, so we can have a really salty diet, for example, that might make our blood have hypernatremia, or the other way is you can get rid of water. We can evaporate off water to make something more hypertonic. If you lose a bunch of water and you don't drink enough, you don't add enough back, you could have hypernatremia. Hypernatremia. So in a word, like one of us said in the chat here, dehydration, the problem with being dehydrated is your blood has hypernatremia, too much salt. The problem with water intoxication, the opposite of dehydration, is hyponatremia. Our blood has too little salt in it. So for the exam, the learning objective asks you to know the relationship between water intoxication and hyponatremia. Basically, what I want you to know is if I drink too much water, that's going to dilute the salt that's in my bloodstream, and that's problematic for me. Because remember, I need my cell to be a salty banana. We got to do a salty banana, right? Like every day of the last few days. Here's my salty banana cell, right? Normally, I have a whole lot of what on the outside? What's there a lot of on the outside? It's a salty banana, right? Yeah, we got that salt, right? So sodium, the first half of salt, fluoride, the second half of salt. And of course, we got that potassium on the inside, right? Normally, I've got a whole lot of sodium and chloride on the outside. The level that I have on the inside is lower. That keeps me from having too much water go into my cells because there's salt on the outside that attracts the water to stay on the outside. If my salt that's on the outside, I'm going to move it away. If that salt moves away, suddenly the salt that I have on the inside looks like it's a lot more concentrated. And if it looks like there's more salt on the inside, because I diluted all of this stuff out here, if that's the case, water is going to rush inside my cells. Because remember, here's something that some of us said in group work. Water follows salt, right? Water follows salt. So if I dilute the solution that's on the outside of my cells, if there's too much water out here because the salt level is too low, what's going to happen is all of that water is going to rush inside my cells. Does anyone happen to remember the name of what I call it when water rushes into the cells? There's a special word for when they swell up. Does anyone happen to know? I'm like way making you think back in the day. I'll help you out because we didn't use that word very much. The word for when a cell or a body part swells because of water, it's called edema. Edema, swelling. So if I dilute, I put too much water on the outside, that water is going to rush into the cells. And remember from our water intoxication article, that's bad news when we talk about cells like neurons, your brain cells. There is nowhere for those cells to, in the words of our chat, right, get big and juicy. If you're a neuron, there's no space for you to have edema. There's no space for you to swell. That's why water intoxication can be fatal. If I swell up my brain cells too much, they're going to die. That's going to be a problem for me. So hyponatremia and water intoxication, you drink too much, there's not enough salt out there. If there's not enough salt out there, that water is going to rush in your cell and explode your cells. Bad news. All right, I went overtime. I appreciate you all tracking with me and sticking with me here till the end. I have covered most of the topics that I got requests to talk about in the review session. So I need you all to do me a favor, either in our chat here now or in the survey that there's a link to on your class announcements. Do that survey for me to help me know what we want to talk about on Monday. We will definitely do a review session Monday morning. If we cover everything we want to, I probably won't do an organized session Monday night. But please let me know what we want to talk about, what we want to review. I am happy to help you out. So either let me know in the chat, let me know in that survey, or you can shoot me an email. Otherwise, good luck to any of you still needing to take exam number 4. Good luck with your final exam preparations.